Welcome everyone. I'm Karthik Jadhav, a research scholar in the Department of WRDM, IIT Roorkee. Currently, I'm also Prime Minister Research Fellow in this department, and I'm also a teaching assistant, PMRF teaching assistant for this course on irrigation and drainage engineering. This course is basically run by Professor Mailapalli from AGFE department, IIT Kharagpur. Okay, so I hope my slides are visible now. These are my professional background. Highlighted that I did my BTech in agricultural engineering from Anand, and then MTech from IT Kharagpur, and currently I'm doing my PhD, and I also work as a junior research fellow. So I want to highlight that if you have any query related to this course, you can directly write email to call course coordinator, or you can also write to me if you have any query by putting subject IDE and write your specific query. So whatever content I am going to cover and what I have covered till now, I am uploading in this YouTube channel, and I request you to watch all videos and material also I am uploading here. So we have already discussed this in last lecture. So let's quickly get to know like what we learn in this week or what we have done till now. So in this lecture, basically we focus on crop water requirement in irrigation scheduling and its related problem. So basically, the lecture timing is in between 4 to 6 p.m. Just wait. Hi Kavya. Yeah, basically the lecture time for this course is on each Saturday 4 to 6 p.m. But due to the health issue for me yesterday, I was not able to take a course or lecture, and that was shifted to 7 to 9 p.m. today. So as I already introduced in first week, let me quickly recap that if you want to learn anything, so according to Bloom's taxonomy of educational objective, there are six learning steps or six cognitive skills that required that basically give us like learning level from low to high. So it's highlighted here. So first we start anything if you want to learn, you need to remember some basic fundamental things. Then once you remember, you will try to understand like okay, what does it mean, how you can use it by applying somewhere, and then you will analyze something, right? And finally, analyzing with different methods, you will evaluate the techniques, and based on your observation for different methods and whatever methods you have developed, you will create new method for betterment or advancement of the subject. Now, let's quickly summarize week one content. So, in week one, we have basically focused on basic status or fundamental of soil and water, and we have found certain problems like there is a high water and food demand by 1.3 billion people, because what is this 1.3 billion people? It's population of India, right? It is approximate number, and it represents 17% of the entire world. But in terms of water, But as I highlighted that in terms of population, India represents 17% of the world population, right? But we only have 4% of the global water resources and only 2% of land surface. In that limited resources, we need to feed 17% of population. And also there are certain problems related to the over extraction of our natural resources, and also like impact of climate change, land use land cover change, and all this impacting severely to our natural resources. So due to that, in irrigation sector or agriculture sector, it uses around 80% of the freshwater resources, right? It means we need to manage it very cautiously to feed future generation and also sustainable development. So considering that, we have started learning about fundamental of soil and fluid mechanics, right? As I highlighted, if you want to develop something, if you want to create some new techniques, you must have idea about fundamental knowledge. So we have started with that, and basically we are working in irrigation and drainage. So where we are applying irrigation, we are applying irrigation in agricultural land. So agricultural soil or land, so that soil have certain physicochemical properties that we must know to understand the movement of water and nutrients in the soil, and that will also help us to decide like when to apply irrigation, how to apply irrigation, which method is best, like that. Okay, so considering that, we have discussed certain important properties of the soil that we must have its knowledge for further learning of this course. And followed by that, in week 2 we have started with the water balance at pilot scale, right? And why it is important to balance water balance, because if you want to measure in hydrological cycle, if you want to estimate any component, any missing component, water balancing approach is fundamental principle. Okay, so this is the water balance approach, like what are the in total system. So consider this soil, what consider this is as a soil water system. Okay, soil with water, right? So if we are when we are considering any system, so that system have certain inputs or certain outputs, and also there are certain storage in between. So in terms of hydrological cycle, it is represented here, and this input component and outcome, if we are balancing it, then we'll able to measure certain parameters like soil moisture, evapotranspiration, deep percolation, whatever we are interested in. And then whenever water will falls from the rainfall or in general precipitation, what will happen to that rain? So that rain will try to enter to the soil surface. Okay, so that first entry of water in the soil, that is known as infiltration. And it is also important to understand about infiltration in irrigation engineering subject. So then we have learned about various infiltration processes. Okay, and how this infiltration processes occur. So there are four components or zone of it. So first zone, that is known as saturation zone. Then second zone, that is a transition zone in which the soil water or soil moisture content will uh, deplete or changes gently, while in case of transition zone, soil moisture content have a constant. And then again in waiting front, soil moisture content will reduce sharply. These four zones are which are very important to understand the infiltration process and infiltration models. Then we have also talked about or learn about measuring of irrigation water. So there are various kind of measurement structure like or certain instruments we are using generally. So for example, flow meter that we are generally using in field. Then also bucket stopwatch for inflow, this most common method, and it easily we can calculate the flow, irrigation flow, but this is the very tedious and uh, laborious, very much labor are required. So generally, and nowadays people are using certain structures like flume, weirs, and this kind of sensors that directly measure the irrigation flow. Next to that, we have also talk about or discuss various kind of infiltration models. So there are in general four general or four most commonly used infiltration models are green and armed, Philip two term, third is Koshiko, and fourth one is Horton. So first model, the green and armed model, so it is best used in a uniform soil with sharp wetting front. Okay, and this is the equation. I'm not going into details, but in green armed equation, they assumes that piston-like flow. Okay, and there is a constant head in homogeneous soil, and it is not valid for long duration or layered soil. So, see, green and armed equation generally used for uniform soil. It means homogeneous soil, and it does not consider layered soil. While Philip two-term equation, so it is generally we are using in a short duration infiltration in lab or theoretical studies, and it assumes the semi-infinite soil, and it also says that sorptivity, that is basically sorption of water, that is dominant in early stage, and it gets steady over the time. And whenever you have a complex field, then that case also Philip two term model is very important. Then Kostyukov equation, so it is empirical, and that used in the field data in a short rainfall events. Okay, and it is simple and easy to calculate because it has certain constant like A and B. Okay, and that we generally decide based on the soil type and other soil parameters. And finally, Horton, that is also most commonly known method and fundamental method for infiltration measurement, and it commonly used in many hydrology and engineering applications. So it fits real infiltration decay well, but have a empirical in nature and requires calibration with the field scale data. And these are the constant of each equation. So this we have already discussed, so I'm not going into detail. And then we move on to the lecture number 7, that is about evapotranspiration. So evapotranspiration is basically evaporation from the soil surface and transpiration from the plant surface. So it's commonly known as evapotranspiration, and in evapotranspiration, we have certain terminologies that are important to know, like potential evapotranspiration, consumptive use, reference evapotranspiration, crop transpiration, or adjusted crop transpiration. So potential transpiration is basically about like transpiration happens when there is a no limiting condition of water in soil. So this is the maximum transpiration that occurred through soil surface in case of no limiting water condition. Then reference transpiration. So in this reference transpiration, we have a certain reference grass crop such as alfalfa, that is of height about 8 to 10 centimeter, and also that surface have a certain albedo around 0.23, and in that condition whatever evapotranspiration is happening, and in this case also water is not in a limiting condition, and whatever amount of evapotranspiration will happen, that is known as reference evapotranspiration. And then we have a crop evapotranspiration. So whenever we will multiply reference evapotranspiration by crop coefficient, so in reference evapotranspiration we have a we have alfalfa grass, and that have a certain property. But if you want to measure evapotranspiration for certain crops like sugarcane, rice, wheat, anything, okay, then you cannot use directly this reference evapotranspiration because this structure, physiochemical characteristics of the different crops have and also they have a different growth stage period, and that leads to different water requirement. Okay, so due to that, if you want to estimate crop evapotranspiration, what we are doing, we are just multiplying this reference evapotranspiration with crop coefficient, that is known as Kc, and soil stress condition. Okay, and then adjusted crop evapotranspiration. So it is again in this we are including management and environmental factors. Okay, to estimate it. Then, if we have talked about factors that influencing evapotranspiration. So, if you see this figure, so crops are in the atmosphere, okay, and some parts in the soil. So, what kind of factors does impact to evapotranspiration? Anyone? Hello, am I audible? Kavya, hello, Soma, am I audible to you guys? Okay, I'm audible. So, if you have any query in between, you can ask me. Okay, just listen. It is also helpful for me, even like if you are getting or not. So, yeah, what we are talking, different kind of evapotranspiration terminologies. Then, factors influencing evapotranspiration. So, factors that is related to the climate, factors that related to the soil, and certain crop characteristic factor, okay, itself impacting this evapotranspiration down. Then we there are also like consumptive use. So consumptive use is basically the water includes that is required by plant for all the processes, and that help basically to sustain the plant. And consumptive use basically exceed the evapotranspiration because it required total use. And but in general, the difference between Cu and Et is less than 1%. Then we have talked about various factor as I already highlighted. I'm not going into detail. And Et measurement. So once we understand like Et is basically water requirement of any crop. Okay, and if water is required by crop, then we must know about like what amount of water uh, any crop is required. Okay. So to estimate that, we have certain methods like direct methods and indirect methods. So direct methods like lysimeter, field experiment, soil moisture depletion studies, and water balance approach, while indirect measurement such as temperature-based measurement, radiation-based measurement, combined measurement, and pan method. And there are a few important methods like based on energy balance approach like FAO 56 method, right? So that are very fundamental and most importantly commonly used technique in at a current stage. And we have talked about lysimeter in detail. So lysimeter are tools in agriculture research and water management that provide accurate measurement of ET by isolating volume of soil and vegetation. So there are three types of lysimeter. So bottom closed lysimeter. So in that we are basically measuring evaporation. Then bottom open lysimeter without crop. So first two one is without crop. So in this what we will measure, we know the amount of water that we are ponding on this surface. So in bottom close case we are getting evaporation, right? In case of bottom open, what we'll get? We get evaporation plus deep percolation because bottom is open. And when we'll put the plant in this with bottom open, we'll get evapotranspiration plus deep percolation and this depth C. Okay. So by balancing water, like if you balance water balance here, okay, if you are inputting C, so C is equal to deep percolation plus plus change in storage. Okay, so how will get this ET? ET is basically evaporation plus transpiration. Okay, so you have evaporation here, you have deep percolation here, right? So from this one, if you'll put this in here in after like say A is equal to evaporation plus change in storage. Okay. So from this you can measure directly evaporation. Then once you put evaporation here, you'll get deep percolation, and by putting deep percolation here, you'll get evapotranspiration. This is a very fundamental method and it's very important at the field scale measurement. And then we move on to the crop coefficient and its importance in crop water requirement estimation. So there are two types of crop coefficient. First is a single crop coefficient approach, so that may not accurately reflect the varying water needs at different growth stage and less precise in regions with significant climatic variation. While dual crop coefficient approach, it is a more complex in nature and it generally require data intensive as compared to the single crop coefficient approach. Then we have also talk about like what kind of direct measurement techniques that are available to measurement of the evapotranspiration. So we have discussed these methods based on temperature data, radiation data, and evaporation data. So based on temperature, there are certain methods like Thornthwaite, SES Blaney-Creedel method, FO24 Blaney-Creedel method, Hargreaves method. Then based on radiation, there are methods like tube, Jason and Hess, Priestley-Taylor, and FO24 radiation. Finally, evaporation based method like that is based on pan evaporation methods or pistons and pan. There are different kind of pans available that we are generally very well described in K. Subramaniam book of hydrology, surface water hydrology. And these are the reference of these methods. So we have also talked about this in details, and then we have discussed about crop water requirement and irrigation water requirement. So crop water requirement is basically water required by crop, while irrigation water requirement includes water requirement by crop plus water required by soil available, water available from rainfall, water losses that is that we need to consider in different irrigation methods. So all that includes irrigation water requirements. So, and it's also important to remember that irrigation water requirement is always greater than crop water requirement. Then we have discussed about irrigation water requirement in detail, right? Like what does it impact and what kind of parameters in detail that are impacting irrigation water requirement, and how to estimate like total irrigation water requirement. Okay, so these are the steps that also we have discussed during our week session. If you have any doubt, you can ask me or you can also write down to the provided email ID. And then in lecture number 9 we have talked about irrigation scheduling. So irrigation scheduling basically means that when to apply irrigation, how much to apply irrigation, and how to apply irrigation. Okay. So first is when to apply irrigation. So there are certain soil based indicator, plant based indicator, okay, that we are using to measure the irrigation water requirement. So based on soil condition or soil based parameters. So in that case, we are uh, Generally, we are using various soil moisture measurement techniques that we have already discussed in lecture number 4 of first week. And then certain methods like uh, plant-based method. So certain methods that is based on plant water requirement, like based on plant temperature, plant leaves water content. So for that we have different methods that we are also using, and certain climatological approach like cumulative plant evaporation or irrigation water by cumulative plant evaporation ratio. Basically, so when to irrigation, so for that we required various measurement techniques uh, based on soil, climatological, and plant indices that give us okay what amount of water is already available in soil, plant, or uh, in this kind of indirect approach. So based on that, what we'll do, we are generally estimating okay this amount of water is must required, that we priorly know that, and based on available water status we estimate the plant water deficit, and calculate okay this amount of water is required by current stage. Now question comes how to apply irrigation. So for that or how to apply irrigation, for that we have different kind of methods, right? So that we'll learn in upcoming week, like furrow irrigation, drip irrigation, basin irrigation, sprinkler irrigation. There are lots number of method. So that we'll discuss, and currently we'll stick to this. So next to that, we have talked about irrigation scheduling, like what kind of technique we can consider. So there are either irrigation we can apply, or we can use deficit irrigation method. So in full irrigation, we are applying in case of where we have lots of waters, like in case of Indo-Gangetic region where we have lots of water, groundwater and surface water. But in South India or other semi-arid region, or specifically Rajasthan, Gujarat, semi-arid part of that region that do not have much water, and farmers must apply or must use their water very precisely. Okay, to conserve it and also like gain the better yield. Okay, so in deficient irrigation approach, what we are doing, we are generally using approaches that provide water at certain deficient percentage of soil moisture, and for that various methods are that we have discussed already in this lecture. And again, in detail, we have talked about when to irrigate, that I already discussed, like based on soil indicators. So there are various irrigation soil moisture measurement technique that generally we are using for this purpose. So with this, we have ended this lecture, and we have also solved certain problems in lecture number 10. So that I'm not going briefly, like that's all obviously related to the crop water requirement, irrigation water requirement, etc. Right. So I'm not going into detail of that. So uh, this is the overall summary of this week number 2 regarding crop water requirement, irrigation scheduling. So before we start question and answer session, if you have any query till now, you can we can discuss it. Okay. So anyone? Rajesh, Kavya, hello. Am I audible? I you can if I'm not like if you have any network related issue or don't want to talk directly, you can also write your queries or any uh, questions or any confusion you have in week number 1 or 2 in the chat box. So I will try to answer that, or we'll discuss that part only that you have a query. Okay. So I request you to write down either in a chat box, or I suggest you to talk directly here. Okay. Don't hesitate, Rajesh. Okay. So you guys are there. So okay, let's move on to the question and answer session. So first question is the method which use only temperature to estimate potential evapotranspiration. Okay, so Lenny Ridley, Hargreaves, Thornthwaite, and Penman formula. So we know that to estimate potential evapotranspiration, uh, all these methods are very important. And uh, this first one, Blanik-Riddle formula, that uses temperature as well as daylight hour to estimate potential evapotranspiration, while Hargreaves equation only use temperature, okay, to estimate potential evapotranspiration. Thornthwaite requires temperature as a primary climatic variable, okay. So our answer is Thornthwaite equation that uses only temperature data, and Penman formula that is a very complex and also known as FAO 2056 or a 24 method, and it requires large complex data of environmental as well as crop characteristics related to the crop characteristics and environmental factors. So our correct answer is option C, Thornthwaite equation. Question number two: water requirement of crop is, so let me draw this here. So whenever you are growing crop, so what is the crop water requirement? So we know that a crop water requirement is basically equal to evapotranspiration. Whatever evapotranspiration will happen in that region, that is, or from this field, that is the water required by crop for their food preparation using photosynthesis method. So generally, this crop water requirement of a crop is generally equal to irrigation requirement plus effective rainfall. Effective rainfall means amount of rainfall that is directly used by crop or that is available for crop water. And if there are any moisture contribution from shallow ground water level, okay, due to capillary rise, that is also the part of crop water requirement. So correct answer is option A. Question number three. Amongst the four distinct crop growth stage of seasonal crops, the maximum value of crop coefficient. So crop coefficient, we know that it is the a fraction, okay, and it generally help us to get about or get to know about crop evapotranspiration using reference evapotranspiration value. So whenever you multiply ET naught with Kc, it will help us to get ET crop. Okay. Now the question is like from this different crop growth stage. So we know that there are four crop growth stage of any crop. So initial stage, crop development stage, mid-season stage, and late season or harvesting stage. And this is the Kc value of different stages. So this is initial, this is development, this is mid-season, and this is late season or harvesting stage. So value of Kc is highest in mid-season stage. Okay, and why? It is like that because mid-season stage correspond to the period of maximum vegetative growth and peak water demand, and during this stage Kc value reaches the highest point as crop fully covers the ground and transpires at maximum rate to produce food. Okay, and if you see that water requirement during initial stage of the crop is minimum because the plant is small, so it is similar to like child. Okay, so whenever child is small, or whenever we are small, so we require less amount of water, but as we have grown up, water requirement, food requirement, that will become more, right? So similar to that, crop also required more water during their uh, mid-season stage where it is well matured, okay, and ready to produce food. So in that stage, it requires more water, and value of Kc is also high. Okay. Now, if the question is like that, in which stage the Kc value or crop uh, coefficient value rate of change of Kc is higher? If question is that, so answer will be crop development stage because see rate of change of Kc is increasingly suddenly, right? So correct answer in that case will be crop development rate. But maximum, if they are asking about maximum value, in that case it will mid-season stage. Okay. Correct answer is option C. And see this again very beautifully drawn. Like first in initial period, crops are small, so it requires less water, and as it grows up, it required water requirement will increasing, and during mid season stage it required more water, and in late season stage it uh, again come to the initial condition when we'll harvest. Okay. Question number 4: identify the appropriate method for direct measurement of evapotranspiration. So we know that Hargreaves, Thornthwaite, and Penman formula this indirect measurement based method, and that requires basically temperature, radiation, and other environmental data. While lysimeter method is most commonly directly used measurement method to estimate or to measurement evapotranspiration. So correct answer is option A. And lysimeter, right? We have already discussed this. So uh, in this say first one as I already discussed in earlier figure, that in bottom closed lysimeter we are generally using to measurement evaporation, and whenever there is a bottom open, so consider this is the open. Okay, both are open. So in that case the evaporation will also open and water also tries to move down. So evaporation first, deep percolation will happen, and whenever there is a crop, so in that case evapotranspiration will happen. So when you will balance all this component, you will get evapotranspiration. So there are also weighing lysimeter. So first one is a non-weighing lysimeter. In case of weighing lysimeter, we have a different components like A, that is soil monolith, or whatever system of soil that we are interested in, and B is the load cell, that is basically weighing mechanism. C is a drainage collection mechanism, and D is measurement of surface runoff being collected. Okay, from this field. So by balancing all this, will help us to calculate evapotranspiration. How we know the hello hello anyone? Do you have any query? Hello, right? So what will happen? We are directly measuring this drainage component and runoff component, and we know that what amount of water we are applying as input from either from as a irrigation or from natural rainfall. And by balancing this input minus output like ET that we are interested in minus deep percolation minus surface runoff. So we know that deep percolation, that is draining, runoff, that also we are collecting, irrigation and rainfall, that will already know based on the what we have applied or what amount of rainfall that fall on particular area. So by putting all this value in this equation, we'll able to measure ET. This already highlighted, right? Change in storage component, it also needs to be incorporated. Question number 5. The evapotranspiration loss of 1 mm per day from 1 hectare area in meter cube is, so we know that 1 mm is equal to 0.001 meter. Total volume of water lost due to the evapotranspiration over 1 hectare area is, so that is area multiplied by this rate. Okay. So area, that is 1 hectare, that is also about 10,000 square meter, and depth that is losing from this area is 1 mm per day. Right. So by multiplying this, we'll get amount is equal to 10 cubic meter. Correct answer is option B. Now, the question shows like which instrument is depicted in the image. Anyone answer? What is answer for this? Have you seen anyone? What is this? So this is rain gauge. Okay, non-recording rain gauge. And rain gauge we are generally using to measure rainfall. Okay, so this is different component of that rain gauge. Okay, this platform, then this the funnel collecting bottle, then we have funnel, and that we are generally putting that water and measure the depth of water. And this non-recording type rain gauge, also known as the Simon's type of rain gauge, and it generally prescribed by IMD in Simon's rain gauge, and it is narrow neck to protected from radiation, right? So this neck is narrow. See this, to avoid losses of water from this collected jar is minimum, and this foundation have certain dimension and also is on certain height to avoid splashing effect. Also there are certain criteria to install rain gauges. Okay, like it should be far away from twice the height of the obstruction or minimum 30 meter of any obstruction, and it basically collect the 1000 mm of rainfall and measuring glass capacity of 25 mm. Okay, and accuracy of this rain gauge is 0.1 mm. Next question, again, which instrument is this? So again, this is the rain gauge. Okay, see, this is the collecting collecting funnel. Okay, and this have a small narrow diameter to avoid evaporation from the collecting jar. While but if you open this, so it have a revolving drum mechanism with pen. Okay, so how it will work? So whenever water will come in this, so it will come to the cylinder. Okay, and due to the siphon mechanism, this pan will rise up, okay, when water will come down. So based on it is calibrated in such a way that whenever what amount, based on amount of water, so it will drawn the graph like this, okay. And once it will come here at top, it will again come down sharply and again start getting recorded. So this is a recording type of rain gauge because it provides at different type what amount of water is falling. And this chart is basically of 24 hours. So in each day, like at 8:30 a.m. or 8 a.m., we need to replace this chart and note down the reading. Okay. So this is recording type of rain gauge, also known as float type of rain gauge, because this, because of this float. Next, which instrument is depicted in the image? So this is pan evaporation, okay, or class A pan, and it consists of 1207 mm of diameter. So its diameter is 1207 mm, and depth is about 250 mm or 25 centimeter. The pan is made of a copper sheet of 0.9 mm thickness and painted white outside, and it's again measure amount based on whatever amount get evaporated, and by adding the water on next day we'll calculate, okay, what amount or what depth of water gets evaporated. Question 9, which instrument is depicted again? So this is Colorado sunken mine, right? So it, again, transpiration evaporation measurement technique, but it generally provide the natural surfaces. So again, see, last one have a heighted one, but this installed inside the soil surface. So that's why what will happen? This measure the actual lake evaporation, right? Because it is it have all the impact related to the that natural lakes that we are generally represent natural lakes, and the coefficient of pan in this case is 0.8. Again, so this is generally known as, this is the box, okay. This box is generally have various kind of dry bulb thermometer, weight bulb thermometer, then minimum maximum temperature instrument, and also humidity measurement. And based on this all this data, we can measure humidity. So this instrument is known as Stevenson screen, and it used to measure this component. And what is this? This is, so if you want to measure, okay, what amount of bright sunshine hour is having in particular region. So as we already shown that the temperature or day length, okay, and what amount of time during the day have a bright sunshine hour, and that sunshine hour directly impacting evaporation calculation. So to measure that, we have this kind of instrument that is known as sunshine recorder. Okay, so it is records the amount of sunshine at given location at any time, and it's also known as heliograph. So it have a paper. So this blue color, this is the chart. Okay, paper chart, and that also again we need to install each day morning, and as the sunlight falls on this, what will happen? It will start burning out. So whatever amount of or length of hour that gets burned during the day, that is generally we need to calculate and remove it down. Okay. Then this instrument is known as, anyone? This is anemometer. Okay, so anemometer generally useful to measure wind velocity. Okay, so in that we have a speedometer. So as winds will blown out, so this number of revolution will count down here, right? And this revolution we have calibrated the distance. So and by calculating like how much rotation is was there and dividing it by time, we'll get wind velocity. Then there's this instrument is known as, so see this is the various direction is shown here, north, south, west, east, and this again fin is there. So this also useful in wind direction measurement. If you want to know wind direction, then this instrument is useful. Then this instrument is known as barometer. Okay, so barometer is generally used to measure the atmospheric pressure, and also that known as barometric pressure. So atmospheric pressure is an indicator of weather. Okay, and changes in atmosphere, including changes in air pressure, affect the weather. So generally, these instruments are useful for meteorologists to predict short-term weather changes. Next question: which leaf area index values are sufficient to maximize transpiration and fully shade the ground? So leaf area index represent the it is dimension dash number and represent the total leaf area per unit ground area. Okay, so whenever crop are small, they have a lower value of leaf area index, but as it's grown, they have a higher, right? So in case of uh, leaf area index of about 3 to 4, right, we have maximum transpiration from that crop canopy. Okay. Next question. Okay, so before we go ahead with this, uh, anyone have any query till now? Hello. Okay, so let's take a 5 to 10 minutes break here, and we'll be back soon. Okay. Next question. Question number 16. Question number 16. Which lysimeter type and dimension are suitable for accurately measuring evapotranspiration in crops with taller and shorter root zone depths? Okay. So whenever uh, crop root zone are taller, in that case we are using lysimeter with depth around 3 meter and 2-meter depth lysimeter for short root zone crops. So correct answer is option C. Question 17. Which method is commonly used to measure consumptive use of water? Tensiometer, neutron probe method, soil moisture depletion method, or pan evaporation method. So tensiometer, we know that it is device that used to measure the soil water tension. Basically, about how strongly water is held to the soil. Okay, so that is known as soil water tension, and that estimated by tensiometer. Neutron probe method. So again, this is soil moisture measurement technique. So nuclear technique to detect the soil moisture by scattering of fast moving neutrons, and it gets slowed down in the presence of hydrogen, and by estimating the back coming slow coming neutrons we are measuring. So exactly, so correct answer is option C, right? Why? Because this method is estimate crop water use, that is basically evapotranspiration by taking tracking changes soil moisture content over time. Correct answer is option C. Next question, question number 18. Which of the following is not a temperature based method for estimating evapotranspiration? We know that Hargreaves method that use the temperature. Brannick Ridley again use temperature and bright sunshine hour, and Cronthwaite also use temperature, while Priestley Taylor Turk method that are not generally using temperature as a primary factor, it use radiation based factors. Okay, so correct answer is option C. Sorry, it is B. Okay, written wrong here. But correct answer is Priestley Taylor method. That is in option B. So it's already highlighted that Hargreaves method that estimate ET primarily based on temperature data, and it considers solar radiation. It's useful in regard regions lacking detailed weather. Priestley Taylor method that used evaporation from saturated surface and often used in ecological study, and it simplifies the energy balance equation by eliminating aerodynamic term. And it used basically radiation data. Then Blaney-Criddle data, so it calculates it again based on temperature and portion of daylight hours affecting plant growth. It means that is related to bright sunshine hour, and it's often used for agricultural purpose and provides simple way to estimate water demand of for crop. And final Thornthwaite, it estimate potential evapotranspiration. Potential evapotranspiration. It means maximum evapotranspiration that occurs from any surface in case of no water limiting condition, and it calculate based on temperature and daylight hours. Okay. Question number 19. What is the primary climatic factor used in Planck-Riedel method for estimating evapotranspiration. So this we have shown in last slide also, like solar radiation and mean monthly temperature. Okay, wind speed that are not used by the relative humidity also not required. Mean percentage of daylight hours and mean monthly temperature. So correct answer is option D, right? Because it required monthly percentage of daylight hours and mean monthly temperature. And this is the equation of Planck-Riedel equation to estimate potential evapotranspiration. Right, and here P means mean daily percentage of annual daytime hours. T mean is mean temperature. Okay, either it is a daily mean temperature and mean temperature. How we can calculate this mean temperature? It is based on T minimum plus T maximum divided by 2. It will give us T mean, and by putting this value we will get ET value using dynamic Ridley method. So there are two parameter required. One is mean monthly temperature and second is P, that is monthly percentage of daylight hours. Monthly or daily, okay, whatever it is based on option that is provided in the question. Next question, in the context of Feynman equation, what does the terms gamma means? So gamma, we know that it is a psychometric constant, and psychometric constant is basically property that relates to the partial pressure of water vapor in the air to the air temperature, and is generally required to interpolate actual vapor pressure from dry and wet bulb temperature readings. Okay, so this is the equation of Monty, and this use various aerodynamic terms as well as climatic parameters to estimate evapotranspiration. Correct answer is option C. Question number 21. Which climate condition generally results in higher evapotranspiration rates when considering crop coefficient value? So, you know that if there is any surface, okay, with like suppose this is the water level present in one bucket. So if this bucket is present in arid climate with low humidity and high temperature. So in arid climates we know that there is a high temperature, and if humidity of air is less, it means we know that at this water surface there is a saturated water vapor pressure, and uh, vapor pressure that occur in air, the difference cause the evapotranspiration. So if this difference is higher, in that case evapotranspiration will be higher. Okay, second, in humid climate with high humidity, so if humid climate is there and even they have a high temperature, in that case in humid climate what will happen, evapotranspiration will not occur at much faster rate, or it will occur very slowly due to that, because this air present in humid climates that is already at saturated level, it means it cannot hold more water. Okay, instead it moves from any way, either it is from up or down or any side. If this saturated air will move down and again fresh air will come, then evaporation will start. So this may be the not the correct answer. Next, windy climate with frequent strong winds and low temperature. So that's again not a correct answer. And windy climate with low winds and low temperature. So correct answer is option A. Okay. So that is arid climate with low humidity and high temperature. Correct answer is option A. Because we know that the aerodynamic properties of crop which influence the ease with which air moves around and through the crop canopy can exacerbate these effects, and especially in open and arid climate with high temperature. Okay, so correct answer is option. Question number 22. Which of the following uh, statement are correctly reflect the relationship between based on general guidelines? We know that crop coefficient value are influenced by crop factors such as crop height, leaf area, exposure to environment elements like wind and sunlight. So shorter crops typically have a lower Kc value, that is less than 1.2, because their surface area and exposure to climatic factors are limited compared to taller crop. While taller crop, in other hand, have a higher Kc value, that is greater than 1.2, as they have a more extensive leaf areas that are get affected by atmospheric parameter. Okay, and they are generally more exposed to like parameter like wind and sunlight that leads to higher rates of evapotranspiration. Right, so correct answer is yes. What is correct answer? Yes, right. So option D is correct. Why? Because no, sorry, there is one there is mistakes. So these are the correct, but maybe I got changed this option here and there. So this taller crop commonly have Kc value greater than 1.2. Right? No, 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 no. So this I think this also correct. Okay, this Kc value is less than 2, and option D is also correct. But let's read question what here it is asked. So which of the following statement is correctly reflect the relationship between crop height and crop coefficient Kc values based on general guidelines? So short crops have Kc value greater than, so this is incorrect. Taller crops typically have Kc value less than 1.2. This is also incorrect. Short crops usually have Kc value less than 1.2 due to lower evapotranspiration demands, and taller crops commonly have a Kc value greater than 1.2 due to increased exposure to wind and greater leaf area. So this option D correctly represent the situation, because obviously short crops have a lower water demand. Okay, but we cannot directly state it, because certain short growing crops like rice they have a higher water demand. Okay, so we can not state it directly, but this condition that is in shown in option D, like taller crops have a higher Kc value that is greater than 1.2 due to this specific region, right? So these options are more representative. Though this, in general, this also right, but more accurate answer is option D. Now, which instrument is depicted in the image? I am talking about here this instrument. So what is this? Do you have any idea? Anyone? So this is known as AWS. That is automatic weather station. Right. So this is automatic weather station is the facility that automatically records the observation like rainfall, minimum maximum temperature, bright sunshine hour, wind velocity. Okay, so all the major meteorological parameters are measured by this automatic weather station, and weather this data is generally collected in this logger. Okay, and this logger is connected with the our system, because this system have a SIM card or Wi-Fi network, so that this data is directly transferred to our system. Okay, and that will directly get to know about current status of weather in any region if we'll insert it. Okay, okay. So till now, do you have any query? Anyone? Kavya? Okay, so let's move on towards. Okay, perfect. So let's move on towards numeric type of questions. Question number one: from long-term average temperature data of a place for May month is 39 degrees centigrade. Temperature T mean is given. The percent daytime hours in a year is 10 for a place, and consumptive use uh, coefficient is 0.6. So we need to measure consumptive use in mm of that region. So first we need to uh, measure the potential evapotranspiration using Planck-Ridley method. Okay, for May month. So it is given by this P bracket 0.460 plus 8.188. So once we'll put T mean and mean daily percentage annual daytime hour equation, will get PET is 261.28 mm, and the consumptive, if we'll multiply this by consumptive use coefficient, that is 0.46, then we'll get consumptive use of particular crop. So this consumptive use coefficient basically similar to the crop coefficient. Okay, like what amount of because this condition PETs represent maximum evapotranspiration. Okay, but it is not the case in each crops, as well as in case of stressed condition, soil moisture stress condition, or smaller crop, different kind of aerodynamic properties. So for that consideration, we are multiplying this consumptive use coefficient. Then based on that, we'll get consumptive use. Okay. Answer is in between 156 to 157. Next question: the saturation vapor pressure at 25 degree centigrade at temperature is 31.7 millibar. The mean actual pressure at 78%. Mean relative humidity in millibar is we need to identify. So we know that relative humidity is given by RH. Okay, so that is actual vapor pressure divided by saturated vapor pressure. Sorry, right. So here relative humidity is given as a 78%. Right. So RH is equal to actual vapor pressure divided by saturated vapor pressure. So actual vapor pressure is we need to uh, So here relative humidity is given is 0.78 or 78%, and this we need to identify, and saturation pressure is given is 21.7. Okay, so once you multiply this with this, you will get actual evaporation, that is 24.72. Next question, 50 kilometer long canal with the width of 25 meter is used for irrigation. The mean daily evaporation is measured from class A pan evaporimeter is 5 mm per day and pan coefficient is 0.8. What is the measured mean daily evaporation loss from the canal? We know that canal evaporation is like evaporation from pan into pan coefficient. So that will give evaporation from any natural water bodies. So for canal, it will be around like by multiplying 5 mm with pan coefficient of 0.8, that is 4 mm per day, this is 0.04 meter per day, and the surface area of canal is generally given by length into width. So length is 50 kilometer and in meter it will be around this, and width is around 25 meter. So total area in square kilometer is square meter is this, and we know the amount of water that is uh, that getting loose from canal, that is at the rate of 0.04 meter per day. So once you multiply by this area of canal 0.04 meter per day, you will get 5,000 meter cube per day, that is evaporation is happening from canal. Correct answer is 5,000. Next question, soil moisture at field capacity is 25%, that is weight of to weight percent, and soil moisture content at the time of irrigation is 15% on weight basis. The apparent specific gravity is 1.25 and depth of root zone is 40 centimeter. How much water in hectare centimeter must be applied to bring soil moisture up to field capacity? We know that soil, we need to determine how much water that is required in hectare centimeter to bring soil moisture up to field capacity. Okay. So first we need to identify soil moisture deficit. So that is about like field capacity minus that uh, moisture content at time of irrigation. So that will get moisture deficient, that is of 10%. And once you convert this moisture deficient decimal, that is 0.1. Then to calculate the water required per unit area, so we know that by multiplying this available water, okay, that is our moisture deficit 0.10 by, because this is on weight per weight by weight basis. So multiplying by this weight by weight basis with apparent specific gravity or bulk density of soil, dry bulk density of soil, will get this moisture content on volume basis. And if you will multiply this with the depth, you will get total volume of water required per unit area. Okay, so this depth is required, and if we convert this depth in a hectare centimeter, so we know that in 1 hectare it is 10,000 square kilometer, and if you multiply uh, just if you want to convert this depth in hectare centimeter, what you need to do, 1 meter depth have a 1 hectare, right? And that will leads to 10,000 cubic meter. And if you'll convert this into the hectare centimeter, that will come around this value, right? And once you'll put this value in this, you'll get 0.05 times 100. means 5 hectares centimeter. Next question. This is about leaching requirement. Okay, so due to the time limitation, I am not explaining this question number 5. I will request you to go through this question and try to solve this by your own. This easy one I will already discuss in lecture week 2. So you go through this once, okay. And if you have any doubt, you can contact me on the provided email ID. So with this, thank you. So basically, before we close up, so let me quickly recap what we have done in this lecture. So in this lecture, basically we have talked about crop water requirement. So crop water requirement is basically water requirement from evapotranspiration. So whatever evapotranspiration is happening from any surface, that is basically crop water requirement. And how to measure that crop water requirement is very important, because based on that we'll plan our irrigation scheduling. So irrigation is a fundamental, and we know there are various benefits of irrigation, but proper irrigation scheduling is required, and for that understanding of crop water requirement is important. So crop water requirement is basically in this lecture we have understood through various evapotranspiration measurement technique, and then based on that how we'll schedule our irrigation. That is basically when to irrigate, how to irrigate, and how much to irrigate. That also we have talked about, and then we have solved certain problems related to these concepts. So in upcoming weeks we'll talk about irrigation water conveyance method and measurement of irrigation water. And with this, thank you so much for attending this lecture. And I would like to request you that if you missed this lecture in any way, you can access it through this provided QR code. So this is the YouTube channel where I'm uploading all the content that I'm going to cover in upcoming weeks, and already I have uploaded lecture of week 1, and I will also upload lecture of week number 2 today once I'll finish this. And I will also upload this presentation in this link with this link. So if you click here in this link, let me show us. This will open to this folder where I'm uploading all the lecture material. Okay, in this folder. So I already uploaded week number 1 PDF. So go through this, and that will help you during your examination, NPTEL examination. Also to quickly summarize and quickly recap during your exams. So with this, again, thank you so much. Thank you. If you have any doubt, you can ask. We can take few queries. Rajesh, Kavya, if you have any query, please ask. So we can take few queries. Hello, am I audible? Hello, something new concepts, and again, thank you so much for joining, and I hope you will join in our next session also and discuss your queries. So thank you. Thank you so much.
Thank you, sir.
Hello. Yes, yes.